In this episode, we focus on three protections that show up again and again in secure AI architecture: identity, secrets, and isolation. These are not fancy add-ons or optional extras. They are the basic building blocks that determine who can do what sensitive keys and credentials are protected, and how well the system can contain damage when something goes wrong. Beginners often picture AI security as mainly about the model producing safe answers, but a large part of real security is about preventing unauthorized access, preventing hidden leaks, and preventing one compromised component from infecting everything else. Identity controls decide which people and services are allowed to interact with the model and the data around it. Secrets protections decide whether the keys that unlock access to systems remain private and controlled. Isolation decides whether different parts of the architecture are separated enough that problems stay small instead of spreading. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Start with identity, because identity is the gatekeeper for almost everything else. Identity means the system can reliably know who or what is making a request, whether that requester should be allowed, and what they are permitted to do. In an AI environment, identities include human users, service accounts used by applications, and administrative identities used to manage models and pipelines. The most important beginner lesson is that identity is not just a login screen. Identity includes how permissions are assigned, how roles are defined, and how access is limited so a user or system can do only what it needs to do. When identity is weak, everything else becomes fragile, because an attacker who gains access can move freely. When identity is strong, many attacks fail early because the system refuses the request before damage begins. A crucial idea tied to identity is least privilege, which means you give an identity the minimum access needed to do its job. If an application only needs to call the model for inference, it should not have permission to change model settings, access training datasets, or view sensitive logs. If a human user only needs to use a chat interface for general questions, they should not have access to administrative tools, debugging consoles, or raw data sources. Least privilege reduces risk because it limits what an attacker can do if they compromise one identity. It also reduces accidental harm because users cannot stumble into dangerous capabilities they do not understand. In AI systems, least privilege is especially important because access to data and model behaviors can create privacy leaks or unsafe outputs even without malicious intent. Another identity protection beginners should understand is separation of duties. This means you avoid giving one identity too much power across different critical functions. For example, the person who approves a model update should not be the same person who can deploy it directly to production without review, because that creates a single point of failure. The identity that can access training data should not automatically be able to change logging settings that might hide evidence. Separation of duties is a way to reduce insider risk and reduce mistakes, because it forces important changes to involve multiple perspectives. In secure architecture, separation of duties is not about distrust of individuals. It is about designing systems so that no single error or compromise can cause a worst-case outcome. Now move to secrets, because secrets are the keys that identities use to prove who they are or to access sensitive resources. A secret can be an API key, a password, a token, or a cryptographic key used to encrypt data. If secrets are exposed, an attacker might not need to break into a system at all. They can simply present the secret and be treated as authorized. AI environments often involve many secrets because they connect applications to model services, connect pipelines to data stores, and connect monitoring tools to log sources. Beginners sometimes underestimate how often secrets leak through everyday behavior, like being accidentally copied into logs, embedded in code, shared in messages, or stored in unsafe files. Secure architecture treats secrets as high-value assets that must be protected with the same seriousness as sensitive data. A key secrets protection is to minimize where secrets appear and how long they live. When secrets are long-lived and widely copied, the chance of exposure grows over time. When secrets are short-lived and limited to the systems that need them, exposure becomes harder and less damaging. Another protection is to store secrets in controlled systems rather than in plain text locations. Even without describing specific tools, you can understand the principle. Secrets should live in a place designed to restrict access, track usage, and support rotation. Rotation means changing secrets on a schedule or when exposure is suspected, so stolen secrets become useless. In AI systems, rotation matters because integrations can run for years, and a secret that never changes is a liability waiting to be discovered. Secrets protections also connect to monitoring, because you want to detect unusual secret usage. If a secret is suddenly used from an unexpected location, at an unusual time, or at a much higher volume than normal, that could indicate compromise. This kind of detection is easier when secrets are not shared broadly. If one secret is shared by many systems, you cannot tell which system is responsible for suspicious behavior. If each system has its own identity and its own secrets, then activity becomes traceable and controllable. Beginners can think of this like having a unique key for each person instead of one master key shared by an entire group. When something goes wrong, you can disable the one key without shutting down everything, and you can investigate with clearer evidence. Isolation is the third pillar, and it is what keeps problems from spreading. Isolation means separating components so that if one component is compromised, the attacker cannot easily jump to others. In AI architecture, isolation can apply to environments, data, networks, and workloads. For example, training environments should often be isolated from production environments because training involves experimenting, importing data, and running complex processes that increase risk. Production should be stable and tightly controlled, with fewer changes and stronger monitoring. Another example is isolating the model-serving layer from direct access to sensitive databases, so the model cannot freely retrieve everything. Isolation does not mean the system cannot function. It means the connections are limited and guarded so movement is controlled. A beginner-friendly way to understand isolation is through compartments on a ship. If the ship is one open space, a leak anywhere can sink it quickly. If the ship has compartments, a leak can be contained to one section while the rest remains functional. In technology, compartments are created by boundaries that restrict communication, access, and privileges between parts of the system. In AI systems, compartments might separate user-facing interfaces from back-end model services, separate model services from data stores, and separate development from production. Compartmentalization reduces attack surface and improves resilience. It also makes it easier to apply specialized controls, because each compartment can be protected according to its risk level. Isolation also applies to data, and this is critical because AI systems can involve multiple datasets with different sensitivity. You might have public reference data, internal business data, and highly restricted personal data. Secure architecture should not treat all data the same, because that leads to overexposure. Instead, you isolate data by classification and access controls so that only appropriate workflows can reach sensitive datasets. This reduces the chance that a model or pipeline accidentally incorporates data it should not. It also reduces the blast radius of compromise, because an attacker who reaches a low-sensitivity dataset does not automatically gain access to high-sensitivity data. For beginners, the lesson is that data separation is not only a compliance exercise, it is a practical security defense. Identity, secrets, and isolation are deeply connected, and strong architecture uses them together. Identity provides the who, secrets provide the proof, and isolation provides the containment. If identity is weak, secrets might be shared or misused, and isolation can be bypassed by broad permissions. If secrets are poorly managed, identity can be impersonated, and isolation boundaries can be crossed with stolen access. If isolation is weak, even good identity controls can be undermined because once an attacker compromises one component, they can move laterally to others. When all three are strong, security becomes layered, meaning failure in one area does not automatically lead to total compromise. This layered design is especially important in AI systems because complexity creates many small cracks where risk can enter. Another beginner misconception is thinking that these protections are only for stopping external attackers. They also reduce risk from mistakes and internal misuse. An employee might accidentally paste sensitive data into a system that logs it broadly, but strong identity and isolation can limit who can see that log. A developer might accidentally deploy a change that weakens a control, but separation of duties and restricted admin identities can prevent the change from reaching production without review. A service might be misconfigured and begin sending too much data to an external service, but monitoring of secret usage and restricted data access can help detect and limit that behavior. These protections are practical because they address the reality that humans and systems are imperfect. Secure architecture assumes imperfection and designs around it. To close, implementing AI architecture protections for identity, secrets, and isolation is about controlling access, protecting the keys that grant access, and containing damage when something fails. Strong identity practices like least privilege and separation of duties prevent unauthorized or unnecessary actions. Strong secrets management prevents impersonation and reduces the impact of exposure through minimization, controlled storage, and rotation. Strong isolation separates environments, services, and data so that compromises and mistakes do not cascade. Together, these protections turn an AI architecture into something you can operate with confidence, because security is built into how the system is allowed to function. This is why Task 10 emphasizes these fundamentals. They are the protections that keep the rest of your controls meaningful.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.